Now we should go further for the core element of the paper, which is the splitting method. Okay, this is the desired, or this is the complete plant. We are having P. If you remember P, this is the scripted P. This is the set of all plants. What we need to reach is this RR and R. What's so called by R? These are the requirements. Okay, these are the total set of requirements that we need to split for the regular PLC and for the safety PLC. I and Q are the images for the input and for the output. So the question is how to split the requirements into, that's what he is mentioning here. We have the total requirements of the system. We need to split them into the regular requirements and the safety requirements. And this is a disjoint division because the intersection between them is a phi. So he will explain that, how to reach that, and he will even explain how from R prime and RS prime we can get RR and IR. This will be a separate supervisor, and this will be a separate supervisor that they will be split, and they will be used to model, or they will be used to control the PLC, the regular part and the supervisory part. Okay, before getting into this, that he is even describing. In 4.1, he will describe the objective of the splitting. And in 4.2, he will describe the splitting procedure. In 4.3, he will prove that splitting does not influence the behavior of the supervisor. I will skip 4.3, okay, and I will skip even 4.4. I will focus on 4.1 and 4.2. 4.3 is somehow theoretical, okay, and 4.4 is related to the code generation, which is somehow out of low impact here because we are just discussing the methodology. So what is the objective of the splitting? For splitting, it's assumed that each condition for a requirement, again the conditions are denoted by C, okay, in RS prime are the safety requirements, is derived entirely from safety BIVs, safety Boolean input variables. Okay, this is something standard in what's so-called PLC open, and it is defined that safety requirements have to be derived from sensors directly instead of internal variables. What does that mean? That for every requirement, because a requirement was a tuple of sigma and C, that belongs to the safety requirements, the location C must be 0. What is the locations of C? We need to review quickly. What's LOCC? It was defined here. LOC returned the set of all location references and set of all Boolean input variables. If the location of C is phi, then there aren't any locations here. That means that this condition does not depend on the states. It depends only on the Boolean input variables or the sensor readings. Okay, and this is one of the requirements in what's so-called PLC open, that again safety requirements have to be derived only from sensors. From sensors directly. It's an important for safety. Okay, each safety requirement has to be a type. So this is a requirement. R1 states that each safety requirement has to be included in the safety part. Okay, each safety requirement has to be included in the safety part. Means that if you know explicitly a safety requirement, it should be included in RS. By the way, what's the difference between RS and RS prime? RS prime is somehow higher level. RS will be derived to design the splitted safety supervisor. So they are not essentially identical, RS prime and RS, and R prime and RR. And this is mentioned above in some place. RS prime may be different RR prime and RS prime are generally different from RR and RS. And we will explain later why they are different. Okay. However, RS prime should be a subset from RS because any safety requirement must be included in the safety part. Another requirement that's in PLC open, which is the safety standard, is that if an output image variable associated with the safety requirement, that variable has to be included in the safety output image. If an output variable is associated with a safety requirement, then it must be included in the safety output image. Okay? The outputs were mainly the actuator signals. So these were the outputs. So if we have an actuator signal that is associated with the safety requirement, then this output signal must be included in the safety output image, must be included in the safety level or the safety layer of the PLC. Okay? So each variable in the output image that is associated with an event subject to safety requirement has to be included in QS. What's QS? Let us have a look. What's QS? QS, this is the division between QR and we divided Q into QR and QS. What's QS again? We return back to the architecture figure. We are having here the image divided into QR and the QS. So if any output here, if any actuator signal is related to safety, it must be what? It must belong here to QS instead of QR. This is another requirement. What else? Due to the safety each variable in the output image, that's all. Due to the safety PLC architecture, events that result in the assignment of a value to a variable in the safety output image has to be included in the safety part. Events that lead to changing the value of a variable in the safety output image have to be included in the safety part. This is the third restriction. Each event that results in changing or assigning a value of QS was the set of the, again, actuator signals. If any event results in changing the value of the actuator signal, then it must be included in the safety part. Okay. Now, finally, there are these requirements that the elements of the safety plans and the elements of the safety requirement should be as small as possible. And the DR, these are the data buffers of DR and DS should be small as possible. IS and QS, these are the input and output images for the safety PLC should be as small as possible. Okay. This means that we should only restrict the safety PLC to be as small as possible. Only the necessary elements. If we are working with R4 to R6 only, we can put nothing in the safety PLC because you are just trying to minimize it as much as possible. However, this is not an acceptable answer because you need to also satisfy R1 and R2 and R3. Okay, so let us have a look at what should be done in the supervisor splitting. So far, we have just finished the requirements or the objective to the splitting. It is encoded in the 6 requirements R1 to R2, 3, R2, R3, R4, R5, R6. Now he will describe how he will do the splitting. Okay. So how the splitting will be done. First of all, we are assuming that RS prime are derived from the safety Boolean input variables. Okay. And the R6 definition of the safety input image and the regular input image are derived. So what's this? He is telling us now that IS, which is the set of the input variables of the safety, is the set of all i's that belong to I capital. I here is not an integer. I is an input variable. Okay? So how to select it from the many variables inside I? I is the set of all input variables, all sensor readings. So how to select those that are needed in the IS? They are selected such that there exists a requirement sigma C that belongs to RS prime, okay, where I belongs to the set of Boolean input variables that are inside C. Okay, I believe that RS prime can be defined initially without any problem. Okay, RS prime is these are the requirements listed in PLC open or the standard safety. So we have them. Okay, so we'll scan all these requirements and see if any of these requirements is related to any input variable inside I, then we will take this input variable and we will assign it into IS. So simply the inputs for the regular PLC will be the difference between the total set of inputs and IS. So simple. Okay, now let us read equation 6. Equation 6 is the output variables of the safety PLC. Okay, this is the set of some output variables that belong initially to Q. This is the big set of outputs. However, how to select these Qs? They have to satisfy the condition that there exists a requirement that belongs to RS prime. Okay, we assume that RS prime is already given because it's given on it's based on the safety standard. We will scan all the requirements in RS prime and select and see whether we are having a B that belongs to B. So what's B capital? We have a B that belongs to B such that sigma QB belongs to TQ. So what does that mean? Sigma QB, this was described above. So B is the Boolean value, or it's a set that is equal to T and true and false. Sigma QT means that when sigma occurs, the value of true is assigned to Q. Okay, that's all. When sigma occurs, the value of true is assigned to Q. So how to read this? Okay. Again, this is the set of outputs that belong to Q, that there exists a requirement, okay, that belongs to RS prime such that we are having some B. This B can be true or false because it belongs to B capital. This B small can be true or false. Such that sigma Q and this true or false belongs to TQ. So what's TQ? We will review what's TQ. Hardware mapping, TQ denotes the relation between an event and a value assignment into Q. Okay, so this is this is TQ. Okay. From R2 and R6, definitions for safety output image and regular output image are derived. So again, what's TQ? We have described TQ. Okay. So we are just, again, scanning all the requirements in the safety requirements. And we identify all the events, okay, that lead to a change in any output, okay. So if there is any output that is affected by an event that is inside that's inside the requirement, then this output is included in QS. Okay, I advise the viewer to read this a couple of times. So we have now QS, QR is just the difference. Okay, now we go to the last one. We need to identify the set of plants that belong to the safety supervisor. Okay, the set of plants are any plant P that belongs to the set of P, this scripted P. such that there exists a requirement that belongs to the safety, because we are speaking about the safety plans, such that sigma belongs to event P. Sigma, where sigma is derived from a safety requirement. Sigma belongs to event P means that sigma is one of the events inside P. So if any plant have a single event that is related to a safety requirement, it will be included into the safety, the set of plants in the safety supervisor. Union, we are having another condition that there exists this 3 tuple of sigma qp that belongs to TQ, such that sigma belongs to event P and Q belongs to QS and B belongs to B capital. Then we will have this PS. It is a union between these two subsets, and as we could see, both of them are related to the safety requirements. So these are the set of safeties, okay, and then we just remove this set from this set, and we take the rest of plants. These are the requirements for the regular. These are the plants in the regular supervisor. Okay. Finally, we need to define the set of event sets for the safety and regular plants, sigma S and sigma R. Sigma S, any sigma such that there exists a plant that belongs to PS, and the sigma belongs to this plant, and vice versa. This is sigma R. And from equations 8 and 10, it follows that all events that are subject to safety requirements belong to sigma S. Okay. I believe so far we have described everything. We need just to explain how to get the regular RR and RR. We need to describe that so we could understand the relations between the requirements. Okay, I will pause just the video here and we will continue in another part.